press the bell icon on the YouTube app and never miss another update.
Yeah, hello dear students. Now let me continue part 9 from center of mass. So I think you learned some integration formulas. Okay. So based on some integration formulas, let me continue some more models. Okay, method of integrations. In the last class I covered a uniform rod of length L whose linear density is varying with lambda is equals to lambda naught x. Okay, and we got finally some 2L by 3 or 3L by 2 we got. Okay, finally. Now next let us continue some more objects. Let us find center of mass of some different objects by using integration method. I told you already. So if you are good in integration, then you are going to enjoy this topic. Okay, otherwise please try to understand, because all these topics are important for JEE level. Okay, otherwise at least you concentrate on the final formula. Okay, if you are good in integration, okay, it's very happiest thing. Okay, otherwise you try to follow it. Now let me continue. Center of mass of a semicircular wire. So write down semicircular wire. Find the center of mass of semicircular wire. Yeah, semicircular wire. Now I am going to find out center of mass of this semicircular wire. If it is a circular wire, we know ring. Circular wire nothing but a ring. Then where is the center of mass? Center of mass is at the centroid. Now the given semicircular wire. See, this is the semicircular wire. Yeah. Whose radius is capital R. Radius is capital R. If it is a full circle, center of mass is at this point. But semicircular wire, center of mass is not at this point. Okay. Here it is varies. Let us see which side the center of mass will shift, where the center of mass is located. To find this type of problems, definitely we have to use integration method. Why? Because we have to take a small element and we have to apply integration. After applying the integration, we will get the final answer. So anyhow, I told you already, there are three terms: lambda, sigma, rho. What is lambda? Linear density. So lambda is equal to what? Mass per unit length. See, is it a linear object or aerial? No doubt this is a linear object. Wire bent into the form of a semicircle, linear object. So we have to use lambda. So lambda is the linear density and m is the mass. L is the length of the wire. So what is lambda now? Lambda is equals to mass per length. What is lambda? Mass per length, linear mass, linear density, mass per length. Now, to apply the integration, let us choose a small portion. See, for different objects, I am going to follow different small elements in a different way. Here from this center, let us suppose this is the O, I am going to find center of mass, in what side is shifted. Okay. Here, at certain point, I am going to take a small elemental. By making an angle theta, I am going to take a small part like this. See, I am going to take a small portion on a semicircular wire. Here I am taking a small part. By making what angle? Theta. Okay, this is the method. So, if this is theta, no doubt what is this? D theta, small angle, very small angle. And here there will be a mass dm. dm is what? Small portion mass, small elemental mass. And if this is r, what is this? This is r, radius. D theta is the small angular displacement, dm. And see, there is an arc length. See, this part will have some length. Total length of the wire is capital L. Total length of semicircular wire is capital L, and this part length is what? Dx. What is that dx? Dx nothing but arc length. Dx nothing but arc length. This is a small arc. And how much the dx, tell me? dx nothing but arc length. Anyhow, for small part, lambda we can write it as dm by small length dx. dm by dx. Then lambda dm, what is dx? r d theta. What is arc length? Arc length nothing but angle into radius. R is the radius, angle is d theta. So dm by r d theta. Is it visible downside? So yeah, dm by r d theta. Then what is the small mass now? Let me write here because I need space. So m is the mass, L is the length. Now let me write here. What is the dm? Okay. Okay, here I will continue. So dm we can write it as lambda into r d theta. See, dm is equals to lambda r d theta. I got small elemental mass. How much the mass? Lambda r d theta. What is lambda? Lambda nothing but mass per length. So dm is mass by length r d theta. What is this L? Length of the semicircular wire. Semicircular wire means what is the length? Pi r. Okay, full circle 2 pi r. Length of semicircular wire is how much? Pi r. So pi r d theta. Okay, I am writing every step here now. Directly we can write. If you know the integration, we can write directly. Direct one step is enough. So anyhow, let me continue. M by pi d theta I am getting now. What is dm? dm is m by pi d theta. I got dm. Then target is to find out coordinate of center of mass. Let us see whether we will get x coordinate or y coordinate, because it is a plane. So there are two coordinates, x coordinate, y coordinate. We can expect x coordinate easily because of symmetry. See, this part are at same distance. Center of mass is here, so there is no change in center of mass. Then there is no x coordinate of center of mass. Only the varying is y coordinate. So there will be a center of mass along y axis. So y coordinate of center of mass is possible here. X coordinate of center of mass is not possible. Don't worry, I will show you both. Okay. So target is to find out xcm, ycm. But xcm is 0. Okay, let us see whether xcm is 0 or not. Here, take this part. See, this part I am taking as a mass. So dm, this is O, and what is this? Theta. This is r. This line I drawn like this. Resolve this r into two components. Resolve the r into two components. What is this component? R cos theta. What is this component? R sin theta. Then what are the coordinates of dm? See, this is the dm. Then tell me the coordinates of dm. One is r cos theta, other one is r sin theta. So x component of dm is r cos theta, y component of the small elemental mass is r sin theta. I got two components, x coordinate, y coordinate. X coordinate is r cos theta, y coordinate, here only we can expect r cos theta, r sin theta. Okay, r cos theta, r sin theta. Now let me find xcm first. xcm, let me write here, observe the steps. xcm, so integration of dm into x component, okay, x coordinate, integration of dm. Let us see the limits. See the limits. Identifying limits is important. What are the limits? So we can start this small elemental mass from here, maximum at the end. So 0 angle to last how much? 0 to how much now? Pi. Okay, you can take this small part here. Next at the end here. If you start here, you will come to the opposite side. Then what is the angle covered by that small elemental part? Pi. 0 to pi. So the limits are very clear. 0 and pi. 0, pi. Substitute dm value. Okay, substitute dm value and x component. So xcm is equals to integration of 0 to pi dm. What is dm? M by pi d theta x coordinate of this dm is r cos theta integration of 0 to pi m by pi d theta. Okay, so m by pi cancelled, don't cancel d theta integration. Okay, I think you know those basics. So xcm integration of, you can write r outside. Okay, this is a integration of d theta is theta. Okay, no need, directly we can expect. Integration of this is cos theta is minus sin theta 0 to pi. So substitute sin 180, sin 180 0, sin 0 0, upper limit minus lower limit. So what is the answer now? Okay, sin 0 0. Yeah, sorry, this is okay. Well, this is cos theta is sin theta. Sin 180 minus sin 0 0. Sin 180 is 0 minus sin 0 is 0. So what is the x center of mass of x component? See, coordinate of x component is 0. There is no xcm. Now y coordinate of center of mass we need to find. Y coordinate of center of mass. So x is anyhow 0. Directly we can expect, because of symmetry there is no shift in center of mass along x axis. Now let me find y coordinate of center of mass. So how to get y coordinate of center of mass? 0 to pi dm into y 0 to pi dm. So 0 to pi, what is dm? M by pi d theta. Y coordinate is r sin theta. This is 0 to pi m by pi d theta. M by pi gets cancelled. M by pi gets cancelled. So d theta becomes theta. Now ycm is integration of 0 to pi. You write r outside. This is theta. 0 to pi. Integration of d theta is theta. R is outside. Sin theta d theta. What is integration of sin theta? Minus cos theta. Okay, you remember all those things. Integration of sin theta is minus cos theta. So r integration of sin theta is minus cos theta. Let me write minus outside cos theta. Limits are 0 to pi. This is pi minus 0. Pi minus 0 is pi. Now substitute the upper limit and lower limit. Minus I written already. Minus cos theta now. Minus I written. So integration of sin theta is minus cos theta. Minus I written outside. So y coordinate of center of mass is minus r cos 180 minus 1 minus lower limit cos 1 0 by pi. So minus minus this is plus. What is the center of mass now? 2r by pi. I am solving very slowly for you only especially. So 2r by pi. Okay, if you are good in integration, you can extend it. Here, my target is only I need to tell the process. Anyhow, finally what I got? 2r by pi. So y coordinate of center of mass means it is at a height of, center of mass is at a height of 2r by pi. Okay, this is the center of mass. For what? For what wire? Semicircular wire, keep in mind. Okay, so practice the integrations. So ycm is 2r by pi. Take this. So next also integration process. Try to follow it, try to practice number of times, then you feel easy. So follow the same methods to solve some JEE level of questions from any type of other textbooks. Okay. Yeah, let me do the next one. Semi-circular disc. Completed? Still wait? Okay. Okay. Yeah. Okay, let me continue now. Take the screenshot if possible. Yeah. See the next object, half disc or semicircular disc. Half disc. Otherwise, semi-circular disc. Semi-circular disc, half disc or semi-circular disc. Now let us get it now. Okay. See, this is the semi-circular disc. Semi-circular disc. Whose radius is r, whose mass is m, length is l. Okay, there is no length, sorry. And this is O. And see, due to symmetry, there is no x coordinate of center of mass for the semicircular disc. Again, what will be there? Y coordinate, because mass is varying along y axis. So, y coordinate. Again, our target is to find out y coordinate of center of mass for a semicircular disc. And see, for the semicircular disc, there will be a value called as sigma. So, what is this? Sigma. What is sigma? Mass per unit area. Mass per unit area. So, area, how much now? Area pi r square by 2. Why? Because r is the radius and pi r square for full disc. For half disc pi r square by 2, then 2m by pi r square is the sigma value. Okay, areal density, sigma value 2m by pi r square. Okay. Now to solve this problem, again you have to go for an integration, means you have to take a small elemental portion and apply the integration with the proper limits, then we will get the answer. So this is the process. So take a small portion. So if I take a small portion like this, see, if I take earlier part, it's not possible. Okay, because everything has to be covered. So let us take like this. See, you take a small part. Yeah. And whose radius, let us take it as small r. Say I am taking this part. If I take number of these type of pieces, if you join all the pieces, you will get a disc. That's why you follow like this. What is r? R is the radius of this small part. And see, dr is the thickness of that piece. And what is the dm? What is dm? dm is what? Mass of that small piece. And see, that small piece is looks like what? Semicircular wire, like a previous concept. If you take that small piece outside, that small piece is looks like a semicircular wire. Okay, so here I take an r, dr, dm. And for small part, sigma we can write it as dm by dA. Mass per area. For small part, dm by dA. So, what is dm? dm is equals to sigma into dA. and dm is equals to sigma. What is sigma? Sigma we got from here. Sigma is 2m by pi r square into dA. What is this dA? Tell me, what is the dA? dA is the area of the small piece, area of this shaded region. Take this piece outside, stretch it on a floor. So take this piece outside, stretch it on a floor like this. What is the length of this piece? If it is stretched on a floor, if r is the radius, length is how much? Length is pi r. Total, if it is bent into the form of full circle, 2 pi r. But how it is bent? It is like a in this manner. So what is the length of this semicircular wire? Pi r. So length into thickness. Thickness how much? dr. So area, this area we can write it as length into breadth. Length nothing but pi r. Pi small r. Breadth nothing but dr. Observe carefully. Pi r dr. Okay? Pi r dr. Followed. Strike off the pi. Okay. Then find dm value first. dm is equals to 2 capital M small r dr this is, okay, by capital R square. I got dm value. Okay, I got dm. Then what is the xcm? Xcm anyhow 0 because of symmetry. Left and right becomes 0. Find y coordinate. Y coordinate. So let me find y coordinate of center of mass. So dm into y dm. And what is this y coordinate? What is this y? Tell me. Okay, before that let us identify the limits. Identify the limits. If you take a very small piece at the center, 0. Last maximum capital R. This semicircular wire starts from 0, maximum up we can take up to here. So maximum value is capital R, smallest value is 0. Limits are very clear. 0 capital R. I think you followed. 0 capital R. And what is this y? That is y coordinate of center of mass of semicircular wire. This is the y coordinate of center of mass of this wire. Y coordinate. Is any x coordinate is available for this semicircular wire? No. 0. Y coordinate is there. Y coordinate means previous answer. What is the previous answer? 2r by pi. 2r by pi. If capital R is the radius, 2r by pi. Now what is the radius of this semicircular wire? Small r. Then what is this y? What is this y? Y is nothing but YCM of y coordinate of semicircular wire. Previous semicircular wire. So this y we can replace by 2r by pi. 2 small r by pi. Small r is the radius. So YCM integration of 0 to capital R. What is the dm? Dm we got it. 2 capital M small r by R square dr into y. What is this y? 2 small r by pi by integration of dm 0 to r 2 capital M small r by R square dr. Okay. Any terms are cancelled? Yeah, 2m. R capital R square. This 2 becomes 4. So YCM 4 let me write outside. Integration of 0 to capital R small r R square, and this pi you write outside 4 by pi R square dr, and integration of small r dr 0 to r. So YCM 4 by pi, this is r cube by 3, substitute the upper limit. Okay, let me write r cube by 3. Okay, r cube by 3, 0 to capital R, this is r square by 2 capital R 0. Then substitute the limits 4 by 3 pi, okay. 4 by pi capital R cube by 3 R square by 2 R square R cube. Now check the answer now. 4, so this is 2 R by 3 pi, verify once. 2R by 3 pi, verify the calculations. Check the calculations. 2R by 3 pi. Answer the given 4R by 3 pi. Anywhere is missing 2R. 2. Check the calculation once. This is pi r dr 2mr. Yeah, these two already cancelled. Okay, be careful with calculations. See, these two already cancelled. Then here what will come? 2. So 2 by pi r cube, and see, this is a 2, this 2 come to the top. So what is the answer? Verify the calculation once. 4r by 3 pi. Check the calculations once again. Here I cancelled 2, again I written 2, here I written 4 earlier. Now that is only 2. So 2 by pi r cube by 3, this 2 come to the top, 4r by 3 pi. Yeah, check it. Yeah, completed. Verify the calculations. See, already same topic is done for second PUC students with a little fast. I didn't solve all these things like this because they know the integration processes. For you, I am struggling now because I think most of the first year students don't know proper integrations. That's why I am struggling here to explain to you. So no problem. Practice the integrations, and here you follow the process, how I am extending. Already same topics are done for second PUC student, outgoing students. That is good. That is very fast. Okay. Anyhow, no problem. Let me continue like this only. Yeah. See the next one. Target the main final formulas. Yeah. See the next. Hollow hemisphere. Hollow hemisphere. So center of mass of hollow hemisphere, like a spherical cup. Hollow hemisphere. Let us try to get the answer for this. Okay. Say hollow hemisphere means like a half cup. See the diagram. Okay, here you try to understand in what way I am extending the problem, I am extending the solution. Okay, that way you observe it first. See, this is the half cup or hollow hemisphere whose radius is mentioned already, capital R. Capital R. Yeah. Whose mass is 1. Okay. And see, this is also the aerial object. So it will have sigma. What is sigma? Sigma is nothing but mass per area. Tell me the area of this hollow hemisphere. For a full sphere, it is 4 pi r square. For a half sphere, 4 pi r square by 2. So, what is the area now? 2 pi r square. Got it? Area is clear. So, I got sigma. Then go for a small element. Let us see in what way we have to take the small element. Okay? See, to solve this question, take a small elemental length on any one side. A. Now at an angle of theta, I am taking a small portion. See, this portion I am taking now. Inside is empty. Inside is empty. Inside is like a globe. Okay, inside is empty. I am taking a small. See, what is this d theta? And what is this radius r? And what is the mass of this part? Dm. What is the arc length? Dx. Okay, this length is what? Dx. Mass is how much? Dm. R. Again resolve some components. And see, this thickness is how much? Dx. What is the dx? Dx is nothing but arc length of this piece. Arc length. Okay, globe you feel. Take a small piece there. So dx nothing but arc length. Arc length nothing but angle into radius. So r d theta. R d theta. Dx is r d theta. And see, in a hollow hemisphere, if I take a small part in this side, this entire part will be covered. 3D. Okay, imagine like this. So this part if I take, entire part will be covered because it is like a hollow sphere. Okay, like a globe. If I take a small piece, it will cover entire thing. So the upper part looks like a circle in shape. See, this entire part will be covered if you take anywhere. See, this entire part is covered. See the upper part. Upper part, if you observe from the top view, if you see, the top view looks like a circle. If you take a small piece, see, take a hemisphere, cut a small piece. Okay, cut it with same angle. By making an angle, you cut the same piece. So you will get one circle. That circle will have some radius. See from the top view, that circle will have some radius. Let us see what is the radius. If this is theta, and see this is the circle. If this is theta, what is this? This is also theta. Use geometry correctly. Theta. R, what is this component? R cos theta. What is this component? R sin theta. Okay? R cos theta, R sin theta. You got the components? R cos theta, R sin theta. So the top view looks like what? Circle. Circle whose radius is how much? R cos theta. And thickness of this circle how much? R d theta, because dx nothing but r d theta. Mass is how much? Dm. Is it visible? Yeah. Now let me write for small part. For small part, sigma we can write it as dm by dA. Dm we can write it as sigma into dA. So dm, what is sigma? Sigma value m by 2 pi r square. dA, area of this ring, thickness and length. Area of that top view means above ring, this part. Area of the shaded region. So what is the area of the shaded region? Length into breadth. Length nothing but circumference. Circumference is how much? Circumference is 2 pi r. What is r? R is not a single r. It is r cos theta. From the top view, if you see, the radius of that circle is r cos theta, then circumference of the circle is 2 pi r cos theta. So 2 pi r cos theta into dx. Length, breadth is dx. What is this dx? Dx is r d theta. Observe carefully. R d theta. What is length? 2 pi r cos theta. What is thickness? dx. What is that dx? r d theta. So 2 pi r gets cancelled. Then what is the dm? Dm I got it as m cos theta d theta. I got dm finally. Okay, I got dm. M cos theta. Okay. So I got dm. Then let us find the y coordinate of center of mass. Integration of 0 to, see I will tell the limits, dm into y component, integration of dm. Identify the limits here. Limits 0 to pi or 0 to 180 or 0 to 90. Tell me which one is correct. So if you take this element up to, if you take this element here, opposite element also covered. If you take here, opposite element also covered. And see, if you take here, opposite also covered. Maximum we can start from here, we can take up to the this point only. So starting limit of this point is 0, ending limit is up to here. So the limits are 0, pi by 2. Otherwise you can take minus pi by 2 to plus pi by 2, you will get the answer. So 0 to pi by 2, 0 pi by 2, maximum we can take up to here. Because if you take here, this point also covered. Okay, from the top view. So 0 pi by 2. Okay. So YCM 0 to pi by 2. dm, what is dm? M cos theta, m cos theta, d theta, y component, r sin theta by integration of dm, m cos theta, d theta, 0 to pi by 2. Yeah, some complicated integrations. So no problem. Here YCM, here let me multiply 2 and divide with 2, because you know 2 sin theta cos theta is sin 2 theta. Okay, otherwise you can apply UV rule, but cos theta sin theta is there now. Let us multiply 2, divide with 2. So I will write 2 here. I will multiply 2 and let me write m outside. Integration of, let me multiply 2 sin theta cos theta. See the same, sin theta cos theta, 0 to pi by 2 d theta, and here m you write outside, anyhow m cancel. Okay, cos theta is what? Minus sin theta, 0 to pi by 2. Cos theta is minus sin theta. Sorry, cos theta is sin, only cos theta is, yeah, what is cos theta? It is sin theta, sorry, every time I am confusing now. Cos theta is sin theta, that's it. Here 1 by 2 sin theta cos theta, sin 2 theta, sin 2 theta d theta, 0 to pi by 2. Sin 180, sorry, sin 90 minus sin 0, this is 1. So YCM is 1 by 2. Sin 2 theta is minus cos 2 theta. Anywhere r is missing? Yeah, r you write outside. This r is there, write outside. 0 to pi by 2. Substitute. Okay, write minus outside. Substitute cos, this is 90, 0. Cos 0, 1, but minus is there. Okay, minus is there. So you will get this entire quantity is 1. This is 1. Okay, use the integration and use the methods. Cos 2 into pi by 2. Okay, cos 2 into pi by 2. And cos 0, that is 1. 1 by 2 minus 1, minus 1 by 2. Sorry, minus 1. So minus minus plus, you will get, just check it. It is only r by 2. Verify this one. Say this is sin 2 theta is cos 2 theta and this by 2 will come because differentiation of 2 theta is 2. So you will get 1. This is 1 plus 1 by 1. So 2 cancel, minus 1. So minus also minus into minus plus 1. Okay, r by 2. So check this value. It is r by 2. Okay. Okay, so let me some more, because next also there is solid hemisphere, solid cone, triangular plate. Otherwise, I will give the shortcuts. Tell me which one. Okay, try. Let us try. So this integration part you verified, so that I can finish the next part easily in a less time. Next, some integration calculation I left to do, so that I can finish some 2 to 3. I will give the methods. Okay, no need to worry about the derivations. Once you are good in integrations, this is nothing. Especially for JEE students. So almost JEE level started already. So chapter started very slowly and entered into so many concepts. So let us try one more now. Let me finish fast. Solid hemisphere. Solid hemisphere. Solid hemisphere. See the diagram. Whose radius is r? Whose radius is r? Whose mass is m? Tell me, for this solid hemisphere, there will be a sigma or there will be a rho? No doubt, it is a volumetric object. So it will have rho. What is rho? Rho is volume density. So mass per volume. Mass per volume. Okay, volume of the solid sphere 4 by 3 pi r cube. Volume is 4 by 3 pi r cube, but this is half. 4 by 3 pi r cube by 2. So 2 by 3 pi r cube. So rho is equals to, volume is 2 by 3 pi r cube. Rho is equals to 3m by 2 pi r cube. This is rho. Now let us see how to take the small element. Okay, next integration you try to solve it. So take the small element. Let us see how to take the small element for this situation. See here, take a small part like this. Yeah, because it is a solid sphere, so you can take like this. At a distance of r, you can take a small part whose mass is clear. See what you are getting. If you take outside, that piece looks like what? Hollow hemisphere. Hollow hemisphere. So if you take this piece outside, it looks like a hollow hemisphere of radius smaller, and this thickness is dr. Mass is what? dm. Mass is dm. Okay, take the small piece outside. Thickness is dr. Mass is dm. Okay. Now let me write for small part. For small part, rho is equals to dm by dv. So dm is equals to rho into dv. So let us see what is that dm. Dm is equals to, what is rho? Rho we got this one, 3m by 2 pi r cube dv. dv nothing but area of this hemisphere and thickness. Thickness is dr. dv we can write dA into dr. Okay, so area of that hollow hemisphere into dr. So area of this hollow hemisphere, how much? Area is generally 4 pi r square for hollow sphere. This is half. Then what I have to take? 2 pi r square into dr. Is it okay? This will give what? dv, small volume dv. Okay, check it. So 2 pi r square dr. Then what is dm? 2 pi gets cancelled. 3m by r cube r square dr. So I got dm. Then you can go for integrations. So I got dm. Okay. See, let me find y coordinate. Integration of dm into y integration of dm. So tell me the limits. This part starts from 0, we can take up to here, and maximum r. So the limits are 0, capital R, 0, capital R. And what is this y? Y coordinate of hollow hemisphere. Nothing but y coordinate of center of mass of hollow hemisphere. What is the formula of hollow hemisphere? Just now we got it. Hollow hemisphere is what? Hollow hemisphere is r by 2. So this is what? Y coordinate of center of mass of hollow hemisphere. What is the value? R by 2. Capital R by 2 is the previous answer. But for this one, how much? This is replaced by small r by 2. Okay, let me write. YCM 0 to r dm. What is dm? 3m r cube r square dr, and y coordinate of center of mass of hollow hemisphere is r by 2. Capital R by 2 is the previous answer, small r by 2, because small r is the radius, and this is 0 to r dm 3m by r cube r square dr. Yeah, 3m r cube cancel, then do it fast now. So YCM is equals to 0 to r square 1 by 2 right outside, r cube dr. Yeah, 3 cancelled already. This is r square dr, 0 to r. So YCM 1 by 2, r power 4 by 4, and substitute the limits, r power 4 by 4. Anywhere pi terms are there? No. This is r cube by 3. So r cube by 3. So r cube gets cancelled. So check the calculations. I am getting 3r by 8. Verify once. Verify the calculations. 3r by 8. Yeah, 3r by 8. At least you target the final formula. Okay, in initial stage, at least you target the final formula. Okay, once first PUC, second PUC means going to complete, at that time, these mathematics things are very easy for you. Okay, starting stage, starting first PUC, okay, it is somewhat tough. Yeah, completed. Yeah, let me give one more. Solid cone and triangular plate. Take the screenshot. If okay. I think completed, because it's already 50 minutes, so let me finish. So I am taking too much time. Earlier I finished all these derivations in a matter of 30 minutes in some other video. For your second years especially, I covered all these things in a matter of 30 minutes. Anyhow, let us try one more. Center of mass of solid cone. Center of mass of solid cone. Solid cone, hollow cone, triangular plate. Okay. So let me draw the solid cone here. So whose height capital H. So in starting classes I written center of mass of the cone like a 3h by 4 something I written. Let us see from the top end. Now I am going to find from the bottom end. This radius is R. Okay. Yeah, this is the solid cone. Solid cone have volumetric density. So rho, mass per volume of the cone 1 by 3 pi r square h. You remember all these things. So this is mass by volume. So keep these formulas in mind. 1 by 3 pi r square h. So what is rho? 3 m by pi r square h. This is the rho. Rho I got it. Is that is visible rho? Yeah. Okay. Now let us go for the small element. So to find this again at a distance of something y, you can take the small portion. So let me take a small portion here. Okay. At a distance of y, I have taken small portion. See, the small portion is looks like what? If you cut a small piece outside, that small piece is like a disc. One slice. Okay, one small slice. So if it is taken out, that is looks like a disc. Okay, thickness is. So what is the thickness? The thickness of this disc is clear. If it is y, what is the thickness? dy. What is the mass? dm. Let us take r is the radius. R is the radius. Okay, this is a h. This is y. Then what is the remaining height? If this is y, remaining height from here is h minus y. H minus y. Take this as a O. Yeah, check it. So use some triangle system. See, from here to here. See, there is one small triangle and one more is a big triangle. Use side by side, base by base from equilateral triangles, from equal triangles. Okay. From here to here, one triangle. From top to the bottom, one more triangle. Use height by height, base by base concept. So what is the height? Let me take small part height. Sorry, this one, base by base. Small r by capital R. I am using simple mathematics. Small r by capital R. Okay, small r. At what height it is there? This is at a height of h minus y by h. Now I got small r value. Small r is how much now? Small r is capital R into h minus y by h. I got small r. Or otherwise, you can write like this. R by, okay, no problem. R into h minus y by h. So r by h, this is nothing but r 1 minus y by h. So I got small r. What is that small r? Radius of that circular disc. This small circular disc whose thickness is how much? dy. Whose radius? r. And we need to find area also. So for small part, rho is equals to dm by dv. So dm is equals to rho into dv. dm is equals to rho into dv. So dm is equals to, what is rho? Rho just now we got it. Rho is 3m by pi r square h is the rho. What is this dV? Yeah, tell me what is dV? dV is the small volume of the disk. So this, yeah, volume of the disk, nothing but area of the disk into thickness. Because that disk have thickness, then that's why I am saying volume. Okay, otherwise only area. If negligible thickness is there, the disk will have only area. Now I am using volume because that disk will have some thickness dy. Disk have thickness dy. That's why dV we can write it as area into thickness. What is the area of the disk? Pi r square. Area of the disk is pi r square. Pi small r square into dy. Yeah, observe carefully now. Pi r square into dy. Okay. So pi gets cancelled. Okay. Pi gets cancelled. Dm is equals to 3m by r square h. What is small r? Small r we got this one. Small r is capital R square 1 minus y by h whole square dy. R square gets cancelled. So I got dm. dm is 3m by h 1 minus y by h whole square dy. So this is dm. I got dm. Target is what? YCM. Okay. So let me find YCM. YCM is equals to dm into y, because it is distance of y, integration of dm. Tell me the limits. What are the limits? Starting is 0, ending is h. So limits are clear. 0 h, 0 h, 0 h. So YCM 0 to h. What is dm? dm is this much. Okay. So anyhow in this there is, okay, dm is 3m by h 1 minus y by h whole square dy into y divided by this integration of dm. You can write m directly, so it is cancelled. So let me reduce the steps now. So YCM 0 to h, you write 1 by h outside. This is 1 minus y by h whole square y, sorry, dy is there. So see, this is also lengthy. This is like a what? A minus b whole square. A square plus b square minus 2ab and multiply y is there. I multiply this y. Apply integration. Means apply the integration for first term, second term, third term. Okay. And substitute the limits. At the end, see I am missing now. At the end, you will get h by 4. Verify these calculations. Okay. Integration you try to extend it, because already it's 55 minutes I think. So h by 4. See, I am missing 2 steps here. Try to do as a homework. Okay. H by 4. Nothing. 1 square plus y by h whole square plus minus 2 into 1 into y by h whole square, and multiply this y. Substitute the integrations, means multiply the integrations and do the calculations. At the end you will get h by 4.